Yeah. So today, all right. Today, part B, Introduction to Systems of ODEs. Starting from today, we will do a lot of linear algebra things. Yes, because last time many students told me not quite familiar with linear algebra. So I plan to do this way. Yeah. At the beginning, I just get to the, our ODE topics directly. Yeah, because if you look at the textbook, the first section, a brief review about linear algebra. Yeah, but I don't want to do that. Although I can do it that way, but usually, when you do not need it, then you do it, you do not get a good impression. Yeah. So I want to do this way. Let's just do our ODE topics. Whenever we need to use some particular properties, then I'll give you a review. Yeah. So today we will do it that way. All right. So let's start with our B.1, the first topic, conversion from an nth order ODE to a system of ODEs. Yeah. So from chapter 3, we just learned, part A, nth order ODE. Okay, yeah, yeah. So we finished that topic Monday, yeah. So now we have that background, but we want to start with nth order ODE. Yeah. This is a general equation. Yeah. All right. Approach. Yeah. Now we take this approach. Yeah. If we can convert an nth order ODE to a linear system of ODEs, then we can apply many tools in linear algebra to solve the higher order ODEs. Yeah. Because if you do not do that conversion, you cannot use linear algebra tools. Yeah, we know there are many powerful tools in linear algebra. Yeah. So here we take that approach. Yeah, so that can greatly improve our problem solving skills. Yeah. All right, so let's look at how to do the conversion. Yeah. Conversion, pretty simple and straightforward. Yeah. Oh, yeah. So here, let me use this one. Yeah, because. All right. Yeah. Understand two types of equations. Higher order ODEs. Yeah. So our higher order ODEs, our solution function y of x is a function of one variable, only one variable. All right. Yeah. And ODE f is a function of multiple variables. Yeah. We view as multiple variables. Yeah. And these, actually, if we look at these functions, x variable, they are not independent, right? They're not independent. Yeah. There are some relations among them, relations. Yeah. But when we look at the structure of this f function, capital F function, we can treat them as independent variables. Okay, so first you use them as independent variables, but they have their own, they have some correlation among them. Yeah. All right. Now let's view on these original solution function. Why? Original solution function. Then, higher order, there are various orders derivatives, all possible derivatives of y function. Yeah. All right, so higher order derivatives on the same function y. Yeah. Yeah. Same function y. All right. Yeah. Okay. Yeah. In general, the higher the derivative orders, the higher the problem. Yeah. In general. Yeah. All right. So now, one common problem-solving method, we want to reduce the orders of the ODEs. If we can reduce the orders of ODEs, then we can make it simpler. Yeah. So here, how to reduce? Question, can we use more functions to reduce the order of the derivatives? Yeah. Because you have to pay, right? So you want to get benefit. So what's the benefit? Order reduction. ODE order reduction. That's the benefit. Yeah. So because after we lower the order, the problem becomes easier to solve. Yeah. Yeah. But you cannot get that benefit for free, right? So you have to pay. Yeah. With some expense. Yeah. You have to. Yeah. The cost we need to pay. We need to use more functions. Here we only use one function, one y function. Yeah. But you need to get it ready with more functions to represent, to help us reduce the orders of the derivatives. Yeah. So let's see how to do that. Conversion to system of n first order ODEs. All right. The goal, convert the higher order derivatives to first order derivatives with more functions. We can only see first order derivative. That's great. Yeah. Even second order, we convert it to first order. So we won't see any higher order derivatives higher than first order. Yeah, that would be great. Yeah, but you need to pay, right? You need to, it's not free. Yeah, you need to do something extra. So we are ready to use more functions to do it, not a single function this time. Okay, more functions. Yeah. So it's a trade-off between orders of derivatives and the number of functions. Yeah. So we take that trade-off. Okay? Yeah. So we feel, because that trade-off, although you may argue we use more functions, but we will get a linear system. We know linear system. That's a nice structure. We have so many mathematical tools that can help us solve linear systems. So that's a nice conversion. Yeah. All right. Straightforward conversion. Conversion, pretty straightforward. Yeah. Not hard to understand. Yeah. All right. Look at this. Y, we just use y1 to represent it. Okay. The first function, y1, yeah, because we need to use subscripts for different functions. Yeah, y1, all right? Then y prime, y2. Yeah. Here you see y1, y2, two different functions, but we know y prime, they are correlated, right? Yeah, don't worry. The correlationship we will address using linear ODE, okay? Linear first order linear ODEs. Yeah. So we will recover. Okay. Yeah. We won't lose the correlationship. Yeah. All right. Then y double prime, y3. That mapping. Okay. That straightforward mapping, and so on. The last one, y n minus 1 order derivative is mapped to yn function. So here we need to use n functions to bring down the orders in the original ODE, higher order ODE. Yeah. All right. Then let's look at the conversion result. Yeah, we need to go back to the original equation. Yeah. Yeah. So here you can see yk equals the derivative of the previous y function. Okay, yk minus 1 prime. Yeah. That relationship. All right. Yeah. Then the higher order ODE we consider is in this form. Okay. Yeah. Not the general. That general form, that k nth order derivative inside, but that one too hard. Okay. So we make it simpler, slightly simpler. So we just consider the nth order derivative of y can be represented as a multivariate function capital F in this way by lower order derivatives and including original function and the variable x. Yeah, we consider this. Yeah, that's already, you know, good enough for us. Yeah. All right. Now, let's rewrite this complicated. Yeah, it looks pretty complicated. Okay, rewrite it in a sequence of linear first-order equations. So we call it a system, a linear system in this way. Okay. y1 prime equals y2. y2 prime equals y3. Dot, dot, dot. y n minus 1 prime equals yn, and the yn prime equals that f function. Oh, sorry. Oh, yeah. So what? Yeah, right. Yeah, yeah. It's a f function. Okay. Yeah. Now this conversion, simple, straightforward. It looks like, you know, not that significant, right? This kind of trivial. Yeah, people can say it's a trivial conversion. Yeah. You know, why it is important, right? Why it is important. Yeah. All right. Yeah. But if you look at the properties, only first order derivatives. Only first order derivatives. Yeah. And linear or not, it depends on your f function, right? Yeah. Yeah. If your f function good enough, then we have a linear function. Yeah. If it's a very bad, complicated f function, then we won't get a linear system. Yeah. All right. Yeah. But for this chapter, we focus on the linear system. Yeah. Otherwise, nonlinear system, we can only use numerical methods to solve. Yeah. Too difficult. Yeah. All right. Next, B.2, basics of linear systems of ODEs. Yeah. Yeah. Standard form of linear systems of ODEs. Yeah. Let's look at the standard form. From an algebraic linear system to a differential linear system. First, let's recall what is a standard form of an algebraic linear system. Yeah. Linear algebra, yeah. No derivatives. Yeah. So it's like this. Okay, algebraic linear system. Yeah, yeah. And here, I just take the n variables, n unknowns, so x1 through xn, n unknowns and n equations. Yeah, this special case. Yeah, yeah. But in linear algebra, not necessary, because the number of equations, number of unknowns, sometimes it could be different. Yeah. But for this class, we only need to consider square matrix case. Yeah. Rows, columns, the same. That's a square matrix. If we write the coefficient, coefficient matrix. Here, short notation, capital A matrix. We use capital A to represent coefficient matrix, rows and columns. Then X, all these X n variables, we're putting one vector, X vector, so we write as a column vector with n components, n-dimensional vector, and a B also vector, the constant vector containing all B components. Now, that's the compact way to write algebraic linear system, like that. Okay, all right. And here I like you, to get used to the structure of the matrix. N rows and n columns. And we use double subscripts. Try to get used to the double subscripts. Okay? The first subscript refers to the row number. Okay? Second subscript refers to the column number. Okay? So 1, 1, 1, 2, row 1. All row 1, 1n. And the different column numbers. When you go to the second row, 2, 1, 2, 2, and so on. So get used to that. All right. Now let's switch to the differential linear system. This time, the left-hand side, first order derivatives of those n different functions. y1, y2 through yn, n different functions. Then the function, coefficient function, so all these little a, they are the coefficient function. Multiply, all those n different y functions. But these coefficient functions, they are functions of x variable. So here, all these coefficient a, they are constant. They're constant. Okay? But that place, they are functions. They are functions. So the difference. Another corresponding to that B part, so we have G functions. G functions. So you can see the structure. You need to extend it, the structure. Then we write the compact form this time. Y prime, here you can see I use, typically when we use boldface, so if you pay attention to the, the way we write, boldface means vector or matrix, not scalar, okay? So these are the scalar numbers, so no boldface. If we write boldface, try to understand either vectors or matrix, lowercase for vectors. Uppercase matrices. So our conventions. So when you see the expressions, what are the vectors and what are the matrices. All right. So y prime equals a times y matrix multiply vector plus g vector. That's the standard form. So that's what we called standard form of linear systems of ODEs. Then we can apply linear algebra tools on this new version of ODE. All right, So that's our preparation. But here, y prime y prime vector, y prime, what's the meaning? Yeah. So vector of all derivatives of those n functions, yeah, and so on, yeah, and the g, yeah, also, yeah, natural way to represent. So all these we call the vector valued functions. These vectors, they are also functions, but they are vector valued functions. Yeah. Yeah. So here you can see, yeah. Try to get used to the new notations. Yeah. We're pretty abstract. But the good thing about abstraction, we can use much shorter notations. Represent something large, complicated. Think about, if you want to write this big formula on paper, how much time you need, right? Takes a lot of time. But if you just write this notation, very fast, okay? Yeah. So only when at a certain point it's necessary, then we write that form. If we can handle in this way, then we just do the calculation using the, short notation, yeah, compact notation, yeah. All right. So in math, notation very important, yeah. But you need to have some kind of abstraction, yeah. All right, yeah. You can handle the abstraction, yeah, we need. All right. Next, free motions of mass spring damped system. Yeah. I want to use the example we learned before. Yeah, we learned this. Yeah. Free motion, mass spring, damped system. It's a second order linear ODE, but here we want to convert it to a linear system, yeah, to give you some concrete understanding. Otherwise, too abstract. Everywhere, abstract notations. Yeah. So you want to see something concrete. Yeah. All right. Recall, so that's the, mass spring system, damped, some damping force, right? Some, internal damping force, not external, okay? Internal damping force. And we know, because here there is no external force. If you look at the picture, there is no external force. That means we should have a homogeneous second order ODE. Homogeneous. All right, that's simple. Yeah. So it looks familiar, right? Yeah. M y double prime plus c y prime plus k y equals 0. M, C, K, all constant. Yeah. All constant. Yeah. So first we can write it in the standard form. Yeah. All right. Yeah. And also, before we convert it to a linear system, we want to write this form first. Yeah. All right. That is y double prime equals this expression. Yeah. Yeah. Not quite that standard form, but so it's a more friendly form for our conversion. Okay? Yeah. More friendly. Yeah. All right. Now we can do the conversion. Y we change to y1. Y prime we change to y2. Okay? Y double prime change to y2 prime. Then let's rewrite the equation as a linear system. Yeah. Yeah. 2, so here, 2 unknown functions, y1, y2. Okay, y1, y2. Okay? Oh, yeah. Yeah. And the first one, second one. Yeah. The second one you can see is a simple linear function. Yeah. So the F, capital F for this one, very simple. Yeah. So we get a linear system. Yeah. Straightforward conversion. Okay? Yeah. You may ask, what's the benefit? Later you will see. So we gradually, we study more and more properties. Yeah. So you will see, you know, this kind of new systems, so we can apply a lot of advanced tools in linear algebra to solve. Yeah. So for this chapter, we will, you know, do that part. Yeah. All right. The general y prime equals ay plus g, but here, look at the g part. Other than y terms, there is no non-y terms, right? Yeah, because here, you know, we cannot call constant terms, non-y terms, the terms not including any y. Okay, so that means the g is 0 here. Yeah. So we here our y prime two-dimensional vector derivatives. Yeah. Yeah. So it's a very simple linear system. Yeah. Two-dimensional vector, 2D vector. A matrix. Yeah. I hope so. You know how to write A matrix. Yeah. Y1 coefficient is 0. Y2 coefficient is 1. Okay? Y1 coefficient negative k over m. Y2 coefficient negative c over m. So you'll write this 2 by 2 matrix. Yeah. A matrix. But G, yeah, from here you can see the G part equals 0. Yeah. G part, you can also see from here, G part equals 0. Yeah. So when G vector equals 0, we have a homogeneous linear system. So it's a homogeneous first order linear system. Yeah. All right. Next, so we want to see characteristic equation. Characteristic equation. Okay? Yeah. From our old second order representation, we can write its characteristic equation in this way immediately. All right? Yeah. But next thing, we want to use the linear system expression to look at how to write characteristic equation. From this time, we use the linear system format to write characteristic equation. Yeah. Because later, when we have a linear system, we don't want to go back to the old form to write characteristic equation. We want to write directly from the linear system. Yeah. Yeah, but that topic, I just delay one slide. After I finish, you know, another 1 or 2 slides, then I come back to look at the characteristic equation from the linear system. Yeah. All right. Yeah. How to see it from linear system. Yeah. All right. So the idea is simple. Yeah, because for the second order homogeneous ODE, we just use, you know, 2 different solutions like that and get a characteristic equation, right? Yeah, yeah, yeah. So when we look at the linear system, we also use the same 2 solution format. Okay, same thing. Yeah, we plug in and see what can we get. Yeah. All right. Yeah. All right. So here the preparation. Yeah. Here y vector, we put 2 possible solution format there. take a derivative, then we apply derivatives on individual functions inside the vector and get that. Yeah. All right. Yeah. All right. Yeah. Oh, here we already work on. Yeah. Oh. Yeah, this version. Yeah. Anyway. Yeah. Yeah. I remember I changed a little bit. Yeah. But anyway, so we just keep going. All right. Keep going. Now, we prepare ourselves with those vectors and a matrix. Okay? Now, let's, plug in those vectors, matrix in our linear system. Yeah. The first thing, we can see y prime equals lambda times y vector. Yeah. Can you see? So this y prime equals lambda because here we can factor these two functions. They have a common factor lambda, right? Common function lambda. You can factor it out for y prime vector. Factor that common factor lambda out. Yeah. So for Zoom students, 3 students. Oh, sorry, 3 students. Yeah, I didn't notice. I didn't notice. Oh yeah, sorry. I need to keep checking. Yeah. Yeah, because I disable the sound. Yeah, next time I try to get a sound. Yeah. All right. Yeah, those 3 students. Yeah. But we recorded. Yeah, those students, you can look at the first. Yeah. 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 All right. So here, what we are doing, for Zoom size students, look at the lambda square. There is a common factor lambda, so we can factor 1 lambda out, right? Yes? 1 lambda out. After you factor that 1 lambda out, we get this y prime vector equals lambda times y vector. Okay? Here, we use a simple property in linear algebra. So here, let me review that simple property. Okay? Review basic properties of linear algebra. Our first basic property we call scalar multiplication of a vector. When we do scalar multiplication, here little a is a scalar number times a vector, okay, x1, x2 components, equals, then you use the scalar number multiply each component inside the result vector. That's the scalar multiplication of a vector. Okay, very simple. Yeah. All right, so then we start from our homogeneous linear system, ODE. Y prime equals a times y. Okay. When you work on this homogeneous linear system, you replace y prime by lambda times y. How about that? Yeah, because we derived y prime equals y times lambda times y vector. Yeah. So we just replace it. Yeah, replace it. All right. So we get this new expression. Okay. All right. Now we are in the linear algebra world. When we do operations, we should follow linear algebra rules. Do not use your arithmetic rules. Okay? Yeah. I'm afraid some of you may just apply the arithmetic rules directly. Sometimes it's wrong. Okay? So when when we have new different rules, I want to point it out. Here, one dangerous operation is don't cancel out y, both sides, okay? Yeah. Don't cancel out, okay? Yeah. In algebra, probably you want to cancel out, right? Yeah, in algebra, but in linear algebra, it's dangerous. Do not cancel out. Yeah. In linear algebra, whenever you want to cancel out something, hold a little bit. Yeah. Because it's very likely it is wrong. Yeah. Very likely it is wrong. Here, if you do cancellation, it's wrong. Okay? Don't do cancellation. Yeah. Even y is a non-zero vector. Yeah, here our y, non-zero vector. No problem. This is our y. Okay? Yeah, for Zoom student, this is our y. Definitely it's not a zero. Right? So if you argue, some students may argue, our y is a non-zero vector, why we cannot cancel out? Yeah. In algebra, non-zero number we can cancel out, right? Linear algebra we cannot. Okay? Non-zero vector don't cancel out. Okay? Yeah. I will show you why. Later you will see why you cannot. Yeah. So because the rules are completely different. Yeah. All right. In order to work on this new equation, linear algebra new equation, first let's write this one. Move to one side. Okay. Yeah. AY minus lambda y equals 0. Yeah. That's okay. Yeah. We just move some terms. Yeah. So that's legal. Okay. That part similar to our algebra, arithmetic, or algebra rules. Yeah, no problem. Yeah, but cancellation that's dangerous. Okay, cancellation dangerous. Multiplication fine. Yeah, multiplication fine, but cancellation. Yeah, yeah. Division, cancellation. All right. Yeah. Yeah, before I continue to work on that form, let's review identity matrix, 2 by 2 identity matrix. Okay? Yeah, our textbook is called a unit matrix. Yeah. But in linear algebra, most of the time we call identity matrix. Identity, so you know the meaning, when you use identity matrix to multiply a vector, no change, right? The vector, the same vector. Okay? So identity matrix here, 2 by 2 identity matrix, because the size could be different, 3 by 3, 4 by 4, n by n. So here we use a subscript to tell you the size of the identity matrix. Yeah. Yeah, our textbook, it does not use size number, just I. Yeah, but you need to, based on the context, you need to figure out the size. Okay? Here I just write clearly, explicitly, telling you the size. 2 by 2 identity matrix. 1, 0, 0, 1. This is identity matrix. Okay? That all the diagonal entries 1 and all the other entries 0. Main diagonal entries, okay? Or 1. Yeah. Identity matrix. So the property is multiplication of the identity matrix and the vector multiply any vector, you get the same vector. No change. So identity matrix does not change any vector when you do multiplication. Okay? Also, when you use identity matrix to multiply another matrix, no change. The same matrix. I2 times A, capital A matrix, you get the same capital A matrix. No change. So that's the, nice thing about identity matrix. Here, why I introduce this identity matrix? Yeah, all right. Because here I need to do an operation. You should be careful. We need to follow special linear algebra rules. What's that? Yeah. So let me ask you in this way. All right. Here we know we cannot do cancellation, as I just said, can we do factorization? We factor y out. Factorization, that's not cancellation. We want to, because y vector is a common factor. We want to factor common factor out. Yes, you can do it. Yeah, it's legal. Factor y out. But the question is, after you factor out that y vector, what's inside the parenthesis? Yeah. This part is A. How about this part? After you factor y out, what's left here? Lambda. Yeah. You cannot write lambda, right? You cannot write lambda. Okay? Yeah. So for, yeah. Yeah. All right. You cannot, yeah, so here, yeah. Yeah. For Zoom size student, yeah. All right. So here, don't write this way. Can you see something is wrong here? Okay. Do not write in this way. Yeah, because here, if you just use your intuition, you factor right out, what's left? Yeah. The reason is this way, why this way is out? Lambda is a scalar, right? Is a number, right? Lambda is a number. A is a 2 by 2 matrix. They have different structure. How can you use 2 by 2 matrix to minus a scalar number? Not compatible, right? When you do matrix subtraction, you have to use two matrices of the same size. Exactly the same size. Then you can do subtraction, right? If two matrices in different sizes, how can you do subtraction? You cannot, okay? So you have to convert the second one with the same 2 by 2 matrix, then you can do subtraction. How do you get the, the second term 2 by 2 matrix? Identity matrix, right? Yeah. So let's write that expression. Yeah. All right. Multiplication of a 2 by 2 matrix and a vector. Yeah. All right. Yeah. So here we review how to multiply a matrix and a vector. Yeah. So it's a new vector. The first component, the first row, multiply the vector component-wise. Okay. Component multiplication and add up those two products. Yeah. All right. So that's the definition of multiplication of a matrix and a vector. So here we do that. Yeah. But when we do that, yeah. So, all right. So here, look at here. All right. Here, lambda y, before we do the factorization, here, okay, so we write lambda y equals lambda times I2 y. That's okay, right? Yeah. Because I2 times y, it's y. Identity does not change any vector, okay? But we intentionally put identity matrix here. Then if you see lambda times identity matrix, you get a 2 by 2 matrix, right? You get a 2 by 2 matrix. Here, we don't have a 2 by 2 matrix. Lambda, all right? Yeah. So let me write this form another step, but I replace lambda times y equals lambda times I2 times y. Okay? Insert that identity matrix because we want to do factorization. Let's see, after factorization, now A minus lambda times identity matrix, now the structure the same, right? The difference of two 2 by 2 matrices. 2 by 2 matrix, A, lambda times I2, another 2 by 2 matrix. You take difference, it's legal. It's legal, okay? Yeah. So that's the reason we need that I2. Otherwise, the previous one illegal. If we do not insert I2, the previous one illegal. Because the sizes, two different objects. Two different objects, you cannot do subtraction. You cannot do addition. You cannot do subtraction. Structure different. Yeah. Here we do the conversion. We make same structure, so we can do addition, subtraction. Okay. All right. After this one, what's next? Here you see one vector times one matrix equals 0. 1 to I2 matrix, parenthesis, that's a 2 by 2 matrix, times a vector. That vector is a non-zero vector, right? Yeah, I mentioned before, this vector is non-zero vector. Okay? Or we say non-trivial vector. Non-trivial. Zero vector we call trivial vector. Non-zero we call non-trivial vector. Okay. One matrix times a non-trivial vector equals 0. What's the conclusion? There is a result I used before. Wronskian. When we do Wronskian, I used the once before. Wronskian. Determinant, Wronskian, not equal to 0. Yeah. So that one. Yeah. We need to go back to that. Yeah. Here, let me give a conclusion first. Then the next slide, I explain why. Okay. The conclusion from this equality, what's the conclusion? Conclusion is similar to our Wronskian condition. Wronskian condition. So I write the conclusion first. Conclusion is determinant of this 2 by 2 matrix must be 0. That determinant, Wronskian is a determinant, right? Yeah? Similar to that Wronskian determinant. Yeah. The situation the same. Yeah. We know, yeah, situation the same. Here we cannot say that's the Wronskian, yeah, but the situation is the same. Yeah. A 2 by 2 matrix multiply a non-trivial vector, non-zero vector equal to 0, then there is a theorem that tells us the determinant of that 2 by 2 matrix must be 0. It's a linear algebra result. Yeah, why? Next slide I explain. I explain it. Next slide. So we can review some linear algebra knowledge. Yeah. So we use this chance to review linear algebra knowledge. Yeah. All right, let me explain that. Actually, at the Wronskian place, I explained once, yeah, but I believe most of you may not be able to understand. So let me explain another time. Yeah. All right. Yeah. Oh, what's wrong? I didn't do animation. Oh, I didn't do animation. Yeah. Yeah. Let me do this way. Yeah, because I don't want to stop here for a break. Yeah, we have about 5 minutes. Yeah. Let me do this way. Yeah. In the break time, let me do the animation. Yeah. Otherwise, too hard to understand. Yeah. But I used the 5 minutes before the break time. Remember, in the part A, yeah, I remember. Part A, there is a topic. Yeah. There is a short topic I haven't finished. Yeah, let me finish that first. Yeah, only one slide. Yeah, so here, let me use the 5 minutes to complete that last slide of part A. Okay, yeah, this one. All right, yeah, this topic. 8.5, analogy of electrical and mechanical quantities. Yeah. All right. So here in the application questions, we did these two types. Okay, mechanical, mass spring systems. Yeah, electrical. Yeah. All right. But if you look at the formulas, there is some analogy between them. Yeah. So let's look at that. Yeah. Here, mathematical model on RLC circuit and mass spring system. There is some interesting one-to-one correspondence. Yeah. Yeah, very interesting. Okay. These two systems completely unrelated. Yeah. One electrical, another mechanical. How can you relate them? But their mathematical models have the same pattern. That's interesting. Yeah. So let's look at that analogy. Okay. The first one, this equation, that's the electrical. Yeah. A typical electrical, system. Yeah. Second order ODE. Yeah. In that way. Okay. Yeah. So, three different terms and the EMF force part. Right. Then the mechanical system, mass spring system with damped force, a damped system, yeah, with external force. This is periodic external force. Now you can see one-to-one correspondence. Right? Yeah. 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 So that's some interesting phenomenon we observed. Yeah. So one from electrical system, another from mechanical system. Yeah. Completely different systems. Yeah. But surprisingly, this table gives us one-to-one correspondence. It's like a perfect match. Yeah. So you can do this match. Inductance L corresponds to the mass M. The second order derivative term. Okay? Yeah. You cannot explain. Yeah, but here we just from the form, we do the mapping, one-to-one correspondence mapping. Yeah. So we don't, here we cannot explain why. Okay? Yeah. Resistance R corresponds to the damping constant C. Yeah. Damping constant C. Okay? Yeah. And reciprocal 1/C of capacitance corresponds to spring modulus K. The spring constant. Yeah. Hooke's law. In Hooke's law, we use that K constant. Okay? That correspondence. Then derivative. Yeah, because this one, yeah, we need to take a derivative. Because for this, in order to get I, we need to take a derivative. So the derivative of the electric motive force corresponds to the driving force. Yeah. Here you can see slightly different. Yeah. So this term, structure, slightly different. Yeah. Then the current I function corresponds to the displacement function y of t. Yeah. Yeah. So after you observe this phenomenon, we want to, sometimes we want to get inspiration from this phenomenon. Yeah. Yeah. Yeah, because these two completely different systems. Yeah. So in the textbook, it describes some situation, so you can take advantage of this phenomenon. So what's that? It says usually when you do physics experiment on the mechanical system, usually not easy to do because a lot of things, the error relatively big. Okay, the damping force, constant. If you measure those quantities, the error relatively big, hard to measure. Okay, so your devices to measure those quantities usually not very accurate. Yeah. But then argue when we measure the quantities in electrical system, so we have many good devices, we can do accurate measure. Yeah. So that means you can do simulation. Okay, when you study this system, sometimes you want to get a better, accurate result. You just convert to corresponding electrical system because you can do accurate measure. Yeah. So that's one argument from the textbook. Okay? So sometimes you can get inspiration. You can get something you can benefit. Yeah. All right, let's take a break. Yeah.